Hello, everyone, and welcome to today's webinar, Practical Enterprise AI, Case Studies from Leading Companies. We have two speakers today who I will hand it over to shortly, but first I'd like to go over a few housekeeping items. Please note that your console is fully customizable, so you can expand or collapse any of the screens. And please type your questions into the Q&A widget. We will be answering all questions after both sessions have concluded. And finally, we will be sending out the recording of today's presentation, so you should receive that within the next couple of days. And at this time, I'll hand it over to our first speaker, Jeff Song, who is going to talk about retail campaign optimization solutions. So Jeff, I'll hand it over to you.
Thank you, everybody. This is Jeff Song from CVS Health. First of all, I want to thank Grid Dynamics for giving me this opportunity to share what I have done recently in CVS. Yeah, here's a very brief introduction of myself. As you can see from the screen, I used to be an associate math professor. That means I was a published mathematician before, a long time ago. And secondly, I'm now a senior data science manager since 2016, working for CVS. And then before that, I worked for 17 years in the financial industry and worked for companies like Capital One and Nationwide. Yeah, frankly, I learned a lot from working for Capital One for 18 years there. And yeah, here's a very, very brief introduction of CVS. In case you don't know CVS that much, it's a Fortune 13th company. Within CVS, there are 4 major lines of business: pharmacy, retail, pharmacy benefit management, and Aetna health insurance. So the mission we have at CVS is like helping people on their path to better health. That's a great thing to do. And then today I'm going to talk about some key solutions that I built myself in the past few years there, and mainly from 8 aspects here. You see, we want to do the right thing. So the strategy is like, hey, for the right customers, we want to offer them the right products through models like a propensity to buy, cross sale, and right channel. So that's for the right production to recommend. And then also we want to recommend the products at the right time, right location, and with the right offers. The right offers means the right discounts. So we are talking about optimization for campaigns. So we want to promote the selling of our products. In order to do that, so we give our customers some discounts. Of course, we expect some returns from that. So it's like a win-win situation between the customers and the CVS. So there are some 8 right things to do. Of course, it's not all of what we are supposed to do, but just listed some of the things I have done here. Again, let me repeat. So the right customers, right products, right affinity, right channels, right time, right location, right offers, and right returns. Okay, thank you. And then, for the right customers, what I have done is like, I built a segment is called investment segmentation for customers. So before this one, we had another version. that was just generated by existing machine learning tools, you know, the Chinese. And then sort of like this is that is about customer clustering. And what I build here is like quite different from that one. So the major objective for me to build this segmentation is like actionable. The previous one I mentioned is like for understanding or profiling customers. Here we want to build something that's actionable for our growth, basically. So there are three major improvements, or put it another way, like you know, different objects for this segmentation. It's like actionable, forward-looking. Forward-looking means predicting to a certain degree, you know, at a certain aspects. And then it's a sort of like for growth targeted. And for growth, that means we want to, again, this is for campaign management, right? We want to promote sellings of our products, and then we want to grow our business. This is very much growth targeted. And ever since it's built like 2 years ago, it's been widely used and generated millions additional dollars, basically, and in both sales and margin. The next thing I want to talk about is like the product recommendation. So when we do the campaign promotion, we want to target the right customer first, right? We have customer segmentation, and now we're talking about, I think, you know, if you want to give them some discounts, what kind of products you want to recommend at first. But then you associate the products with the offers, okay, the discounts. So that means the first step is like what products you want to recommend to be recommended together with the, you know, appropriate discounts. So, you know, I designed a package for it. Let's say for customers, you know, in the past 12 months, for the products we purchased, I have a propensity to buy model. For the products we never purchased, and I have a cross-sell model. And then let's see, timing-wise, you know, most of the retail products, they are seasonal, very seasonal. So there is a timing issue for that. And for that, I built the seasonality model. Okay. Methodology-wise, the models I built here, you know, I developed my own algorithm. It's like an unsupervised. So the major difference between the models I built compared with the previous versions is that, you know, for the models that I built, so whenever you use it, let's see this week or next month, the model will be automatically updated. Or in another way to say is that like the model will be automatically rebuilt. What's the benefit of that? So that means the models I built here has a self-learning capability on the new trend. So let's say, you know, the trend in the past 3 months versus the models built in a traditional way. I use historical data a year ago. It's only captured the trend a year ago. It's not the trend happened in the past 3 months, things like that. Okay? Yeah, it's being widely used. And then, yeah, the last topic I want to talk about is like the offer optimization. So once we recommended the right products, and then naturally we associate that with you know, appropriate offers. So what kind of offers is optimal for the customers? So we, you know, we tried many weeks before this variant. Let's say at least 6 of them, and then they were not working satisfactorily. So based on the learnings, based on the data mining I did, it's like a, I sort of like have a very good understanding of the customers' shopping behavior, redemption behavior, the campaign objectives, and also like digging into the methodologies used before and come up with a new version here. So it's it's gaining like $35 million annually. This one, senior management was super excited about this result here. I would say methodology-wise, before it was direct targeting, so we want to get lifts compared with our campaigns without using the model. So we want to get actual lifts. Right? So using this model without using this model, we want to calculate the benefit of using the model. That's called the lifts. In the previous methodologies, are forecast on are targeted on the KPIs, the campaign lifts, and then there's a problem. You calculate the lifts, you have to use samples of a group. So that means the lifts are based on group of customers. We compare the test with the control. And then if you build a model, you need to split the samples. The smaller the samples are, the less reliable statistically the KPIs are. So understanding that kind of a problem, I designed another way. So let's say an indirect targeting. I'm not targeting the KPIs we wanted to measure anymore, indirect. And then completely this time from a customer level rather than from a group level. And then it made a huge difference. I designed a package, some model components, not just directly using any existing algorithms. So the results is pretty good, and then it's being implemented. So of course we are still learning and trying new things like a reinforcement algorithm and some other advanced and recent developed ones as well. We'll keep learning. Thank you so much. I will be happy to answer whatever questions you have after the break. Thank you so much. Bye.
Thanks so much, Jeff. And again, a reminder to type your questions into the Q&A widget. We'll be answering all questions after both sessions have concluded. And at this time, I'm going to turn it over to our second speaker, Ilya Katsov, who is going to talk about improving personalization using reinforcement learning techniques. So Ilya, I will turn it over to you.
Hello, thank you for joining this Data Points webinar. My name is Ilya Katsov. I'm a head of data science at Grid Dynamics, and in this talk, I will be focusing on how we can improve personalization using reinforcement learning techniques. So first of all, let me briefly introduce Grid Dynamics. We are a data science and software engineering consulting company headquartered in Silicon Valley, and we work with many retail, manufacturing, technology, and finance companies, helping them to execute innovative programs, in particular related to data science and enterprise AI. And more specifically, we work with them in the area of customer intelligence, personalization, price optimization, supply chain management, risk management, and so on. And in this talk, I'm going to focus on some lessons that we learned from this project. So essentially, the agenda for this webinar is, for this session is very simple. We first will try to answer the question, why do we need reinforcement learning for personalization applications, and how reinforcement learning can help us to improve our personalization solutions. And the second question is how exactly we use reinforcement learning to build such solutions, and in particular, how we use reinforcement learning to build next best action solutions. For the second part, I'm going to provide two case studies. First one is about the project related to building next best action for consumer packaged good promotions. And the second case study will be about building next best action solution for digital media products. So first of all, let's start with some context, how we typically build personalization systems, and what are the use cases, and what are the limitations of traditional personalization algorithms. So first of all, let's consider the traditional approach to building personalization solutions. We typically start with some customer data that can include some demographic information, that can include some behavioral information like clickstream or history of orders, history of transactions. And then typically we engineer some customer features in an aggregated way, like frequency of purchases, recency of purchases, and so on. And we can also use some features that are produced out of product information, like product textual descriptions, product attributes, even product images. And then we have some target variable that we are trying to forecast, we are trying to estimate. It can be probability of click, it can be probability of offer redemption, probability of conversion, total lifetime value of a customer, and so on, depending on what kind of problem we are trying to solve. There are different algorithms that are applicable to this problem statement, ranging from lookalike modeling to collaborative filtering to survival analysis to clustering to anomaly detection, depending on a specific use case. And each of these algorithms, in general, applicable to a number of use cases. For example, we can use lookalike modeling to do promotion targeting, or we can use collaborative filtering to do product recommendations. But in general, what we are trying to do, we are trying to learn this function, this dependency between user features and our outcome variable. In this problem statement, it works very well for many applications, and it is of course widely used all across different industries, but there are a number of limitations with this problem statement, with this approach. So one of the limitations is related to how we interact with the customer and how we optimize our strategy with regard to interacting with the customer. So in general, interactions with customers represent some sequence of events. We can provide one offer, we can receive some feedback from customer, either redemption or not redemption or some other action. Then we can do some other action, like provide next promotion or do something else. And in general, we need to optimize the whole sequence of interactions, as opposed to just optimizing one single outcome, like one single conversion or one single probability of a click. The second challenge is that environment can be dynamic. We not necessarily have all this historical data, and this historical data are not necessarily relevant in rapidly changing environments. For example, if we have a lot of new customers or a lot of new products, then historical data might not be really representative. Which is especially true in environments like news feeds. There are things are changing very rapidly, and in general, we need to not only to learn from historical data, but to actively explore the environment through interacting with customers and collecting some feedback information, and then using this information to update our models. And finally, the third problem is that this approach with aggregated features is generally tractable, but it requires a lot of manual work. It requires to define these features, to test feature significance, to select relevant feature sets, and train the models and validate the models and so on. And the natural question that we can ask, if we can use some advancements in reinforcement learning, that we have agents that interact with the environment, and they collect some feedback information dynamically and update themselves, how we can leverage these advancements to these problems so we can avoid these manual steps at least partly, and eliminate some complex feature engineering, or eliminate some complexities of this traditional modeling process. And in this talk, I'm going to focus on these 3 problems. And as a running example, I will use promotion optimization, which we solved many times for different clients. And I'm going to talk about 2 projects that demonstrate how some reinforcement learning techniques can be used for this problem to address these challenges and to improve traditional solutions. So first of all, let's talk a little bit how we can design our target metrics when we are doing promotion targeting and promotion optimization. Because to some extent, the problem of strategic optimization as opposed to myopic optimization can be addressed through sophisticated target metric design. Typically, when we are doing some sort of promotional campaigns, we have some business goal in mind. We're either looking to acquire new customers, or we're looking to grow existing customers, maximize their consumption, or we're looking to retain customers who are at risk of churn. And in general, each of these problems can be decomposed into some statistical problems and some targeting rules. For example, if we are looking to acquire new customers, then we in general looking for customers who are non-buyers of our products at the moment, and we can determine it based on the information that we know about this customer in many cases. And then we need to calculate the propensity score. What's the probability of this customer to buy our product? And in general, this can be done using lookalike modeling. And the same thing for maximization and for retention. In that cases, we are looking for customers who are currently buyers of our product, but they have high probability, high propensity to buy more, high propensity to buy less, or to switch to a different brand. And then once we have this business goal defined for a specific promotional campaign, we have quite a lot of flexibility in how exactly we design target labels, target metrics that we would like to estimate and then use for targeting decisions. In the most basic form of lookalike modeling, we can just focus on immediate outcome, like the probability of click, probability of purchase, and we essentially trying to estimate this value based on what we know about the customer. So we essentially trying to estimate the probability of response to an offer given customer attributes. In a more advanced schema, we can combine this estimate for the probability of click or probability for conversion with some monetary metrics like lifetime value of a customer, which can be calculated by a separate model based on customer attributes. For example, it can be defined as long-term spend of a customer. And we can even extend this model in more advanced ways. For example, we can estimate not only the probability of response to a certain treatment, to a certain promotion, but we can actually measure the difference between the probability of response provided that we treat customer with a certain offer or certain promotion, and probability of response provided that we do not treat customer with this offer or promotion. And then we can target customers with high difference between these 2 probabilities, and we can mix lifetime value estimates into this model as well, and so on and so forth. But the problem is that we're still focusing kind of on just one single outcome, and it's not really straightforward how we can optimize the sequences of interactions with customers. And one possible way how it can be done is to build many models for different offers and incorporate historical interactions with the customer. So if we, let's say, we have a sequence of offers, and we're trying to build a model or a set of models that helps us to optimize the whole sequence of these offers, then we first can build a model for the first offer based on historical profile for what we know for the customer, using some of the techniques that we just talked about in the previous slide. Define our target variable, train the model, and then this way we will be able to pick the best offer for beginning the sequence. So next, once we have this first model done, we can train the second model, and for the second model we will have information in the customer profile about the first offer that we offered before the second one. Again, train the model that will be conditioned on the fact that we already provided a certain offer to the customer, and estimate our metric of interest like lifetime value or the ROI of the campaign. And so on, and then we can repeat the process and build multiple models like that. And actually, in one of the projects that we did for CPG marketing agency, we implemented a solution initially in exactly the same way as a collection of models, but it was very challenging to maintain all these models and to retrain them in a consistent way, and the whole solution, it did not look optimal in terms of algorithm selection, because it looked essentially like a naive approach, and we started to look if we can do better than that using some techniques that are originally designed for strategic optimization. And of course, we quickly realized that we can use some sort of reinforcement learning techniques, because reinforcement learning is fundamentally based on the concept of markup decision process. It essentially represents the environment with which we would like to interact and for which we would like to optimize our interaction policy as a sequence of states. So at any point of time, our environment, and in our case, environment will be our customer, can be in one of states, and we will have essentially infinite number of states, because each customer vector, it corresponds to its own state, and we generally can have unlimited number of states. And then customers can transition over time from one state to another, and for each of these interactions, for each of these transitions, we generally need to take some action, for example, provide a certain promotion or provide no promotions. And during this transition, we will also earn some reward, which can be, for example, revenue that we are getting over a certain time period, like a week or month from this customer, right? And then our goal is essentially to learn some policy that tells us what sequence of actions we need to take to transition across the states in an optimal way. And of course, each state that will contain some information about actions that we took before we arrived to this state. In other words, we are in this representation, we are trying to learn some function that maps our state, some customer representation at a certain point of time, and some action representation, which generally some representation of our offer, of our promotion, of this offer features, what kind of offer it is, what the discount amount, and so on, to the metric of interest that can be, for example, lifetime value of a customer. And then we can do optimization on top of this function to determine what's the optimal action selection policy. And this was a kind of theoretical background of how we can frame the problem, and the way how we implemented this idea. It was relatively simple, relatively straightforward. We used what is called fitted queue iteration, and let me illustrate this approach with the following example. So let's say that we have a number of customer profiles, customer interaction histories. So in this heat map, every line corresponds to one customer, and we have several hundreds of them, and each dash corresponds to one event within the history for a certain customer, which can be no action, which can be a store visit or a purchase. And in these histories, we actually we picked the time frame where all these customers were exposed to three different promotional campaigns approximately at these time frames, right? And the way we can apply fitted queue iteration here is that we can split these customer histories into tuples. Each tuple will represent a state, action, reward, and new state. So, for example, we can take for the first promotional campaign, we can take this part of customer history and aggregate it into a state vector. Then the offer that we provided to the customer will be our action in this tuple. Then we will observe some reward during the next time period, which can be a total number of purchases, a total amount spent. And then if we aggregate the customer history for 2 time intervals up to the second offer, then it will be our new state. And then what we can do, we can first somehow initialize our state value function that maps customer state and action to expected reward. And then let's say that we define some training set, which is initially empty, and then we take all these tuples that we obtained through cutting our customer histories into these chunks with state, action, reward, and new state. And we first initialize, for the first iteration, we define our training label just as a reward. We essentially trying to predict our reward just based on the customer state, one step ahead. And then we take these tuples, and for each tuple we take state, we take action, concatenate them together into our independent variable, and reward will be our training variable that we are trying to learn. We add it to our training set, and then we use some supervised learning algorithm, which can be anything ranging from linear regression to neural networks to gradient boosted decision trees to learn how to learn the dependency between state, action, and this target variable. This way we can essentially build a basic targeting model that is essentially identical to traditional lookalike model. But then we can start to repeat this process. We can reinitialize our training set, and then for each tuple that we have from these customer histories, we can redefine our target variable as our reward for the next step, but also our estimate for the value of the state and action that we are going to take in this state. And this way we will be optimizing on the second iteration, we will be optimizing or we will be learning our reward for 2 steps ahead as opposed to just 1 step ahead. And then we will repeat the process, we will fit our model again, but this model will estimate the reward that we will be obtaining over 2 time periods, provided current state and provided that we take optimal action from this predictive model standpoint. Right, and we just repeat this model iteratively. It's essentially like a generalization, like extension of basic lookalike modeling. And this is what we implemented, and we figured out that it actually can be quite helpful for these types of applications because it's relatively easy to implement, but at the same time it helps us to optimize our interactions with customers in more strategic way, as opposed to doing it just for 1 step ahead. So here in this slide, I have some examples that show more clearly of how we can use this state value function. So, for example, if we take some subset of customers, and each customer is represented by its multidimensional state vector, and let's just project this state vector to some 2-dimensional space so we can visualize it nicely. And then we do this projection, and then we color code our subset of customers based on maximum value that we can achieve in their corresponding states, provided that we pick optimal action from our model standpoint. So, and here in this example, we see that, and then we can do some analysis of what these states actually represent. And here we can see that we have these clusters of different customers. And if we do analysis of what these customers have in common within each cluster, then in this example, we figured out that, for example, these customers and these clusters, they have in common that they got offer number 3 in early stages. So we had this the sequence of campaigns with 3 offers, right, as we talked in the previous slide. So, and for these customers, the value that we expect from them is very low, and it tells us that basically offer number 3 is probably not a good offer to start with, because it doesn't matter which action we take, and we are trying to take optimal action, we will not get high value from these customers. At the same time, customers who did not get any offer got offer number 1, they have higher value, and customers who got offer number 2 early in their stages, they have even higher value. And finally, customers who got offer number 2 and then offer number 3, they have maximum expected value. So which generally suggests us that the sequence of offers, offer number 2 and then offer number 3, is a good combination for this subset of customers. And even we can do it even more formal and even in more automated way if we plot not just the value of our function, but if we plot action that this model essentially recommend, action that maximizes the expected return from the action that we take, then we can see here that customers for this group of customers who did not get any offer or who got offer number 1, the system will recommend them offer number 2, but not just based on myopic considerations, but with a goal to move them to a different state in which the system will recommend them offer number 3, and then it will move them to the state with the maximum value. And this way the system understands how to optimize interactions with the customers in the strategic context in this case. So this was one of the first projects that we did in the customer intelligence and personalization space using some sort of reinforcement learning techniques. It was very basic. It was not like really reinforcement learning. It was we essentially implemented just one aspect of it, this fitted queue iteration to make more strategic optimization. But in general, it was beneficial because we observed some uplift comparing to just basic lookalike modeling that optimizes offers without this strategic context. And now let's talk about the second project, the second case study that we did for a digital media company. So in that case, we took a very different approach. The problem statement was quite similar, that this digital media company, they were looking to optimize promotions, optimize offers for customers, and they also were looking to do it in this strategic context. And but at the same time, they were looking to try some new technique that will not require that many, that high amount of manual modeling of this feature design and doing all these traditional steps and applying fitted queue iterations, for example, as we did in the previous project. And the approach that we took in this project was to use the Agent reinforcement learning platform that was originally developed by Facebook and then open sourced. And at a high level, this platform, it provides a very different perspective on how we can use reinforcement learning. It's very different from what we just talked about in the context of the previous project. So essentially, the idea here in this platform is that let's say that we have some transactional system. It can be our web application, it can be a mobile application, it can be something that interacts with the user, and then we can write some logs from the system that can include all the information that generally needed to apply reinforcement learning style policy learning. So in general, it can include information about current customer state, which transactional system generally knows from its customer database. And it also can write the action, typically meaning like offer ID that was provided to this customer, and also other possible alternatives that the system would consider, and the probability of taking this alternative. So this information about alternative actions and their probabilities is not necessarily available from the beginning. For example, if we are using some rule-based system, it just takes some action and it's not necessarily provide any probabilities for alternative actions, but I will talk how we can work around this problem in a moment. And finally, the system can write some reward that was obtained from the interaction with the customer, like did customer click on the offer or not, in this log as well. Or we can collect this information about reward sometime later if it is not immediately available. And in some applications, it's not immediately available. For example, if we just distribute offers, we do not immediately know will customer redeem this offer or not, and we can get this reward information only sometime later. And then what the system does, it essentially does some pre-processing of these logs, but then most importantly, it replaces these logs against reinforcement learning agent, something like DQN agent, and this agent learns the policy that optimizes what actions we are taking based on the current customer state with regard to the reward. And then this model can be evaluated by the platform. Some metrics can be calculated that can provide us some sort of insight or even guarantees into performance of this model. And then the model can be exported out of the platform as a torch script and deployed into transactional system. And then we can collect more data under this new policy. And in that case, this policy will also provide information, of course, about actions that it took, but also about probabilities of alternative actions, which we generally need to train our next iteration of this policy. And then we repeat the process iteratively and deploy new generations of our policies in production. So this is how it's supposed to work at the conceptual level, but when we started to implement it in practice, we faced many challenges, and here I'm going to provide a brief summary on what were the challenges and how we worked around these challenges. So first problem that we faced was, of course, how do we bootstrap this system? Because initially we had just a rule-based offer personalization system, legacy system, that did not provide any information about alternative actions. And this information is needed for policy training, because if we train some new policy using these logs collected under some old policy, we essentially doing this of policy training, then we need our old policy, our behavioral policy under which we collected this log to cover all essentially like all possible actions in order to create a comprehensive new policy that is able to explore all possible actions and make some meaningful optimization. But it was not the case initially, because we did not have probabilities for this baseline policy. And to work around this solution, what we did, we built an auxiliary click model that was essentially a lookalike model that approximated probabilities of selection of a certain action based on the legacy log. So essentially, if we have rule-based policy, it has probability of 1 for a certain action and probability of 0 for all other actions. But if we build a lookalike model, then in lookalike model we can, if we do it, then we can essentially estimate what will be the probability of conversion, probability of order redemption, if for different offers. This is typically this click model. It will give preference to the same offer that was selected by rule-based policy, if this rule-based policy was well designed, but not necessarily. And it also can tell us that there are some alternative actions like second best action or third best action that will also potentially give reasonable rewards if we apply them. So it essentially like smooths these binary decisions that were done by rule-based policy, of course, in some approximate way. And then we can use it to estimate our probabilities of actions and feed them into the agent and train the agent and produce our reinforcement learning policy. So this was one of the key techniques that we used to make this solution tractable in practice and bootstrap the system. The second problem that we faced was how do we evaluate the model and how we can obtain some performance metrics for the new policy that we train using reinforcement learning agent. So conceptually, it can be done using reagent platform because it provides some built-in estimators that can estimate performance of the new policy. Generally, these estimators are based on some sort of importance sampling, but importance sampling again, it requires to collect logs under some good behavioral policy that covers our space of actions pretty well and provides the probabilities for these actions as well. And in our case, it was not really possible because this baseline rule-based policy, it was not very good. The actions that it used to take were not optimal, so there were a lot of discrepancies between actions that were actually taken under this behavioral policy and actions that our click model recommended and our agent eventually recommended. So there was a very limited overlap between actions that were originally taken by behavioral policy and then were chosen by our agent, our reinforcement learning agent. So it was not really possible to apply importance sampling in this case efficiently. So what we did, we essentially decided not to pursue actually good estimators for the policy that we learned, but we decided just to measure some secondary metrics, basically how well our agent approximates our click model and how quickly it's able to learn how to approximate it, because we're training it in this essentially like log replay simulated environment, so we can measure how quickly it learns. But after launch, we started to collect new logs with probabilistic distribution of all actions under our reinforcement learning policy, and this enabled us to use importance sampling. And we are still working actually on this project, and we are still, still in the process of collecting this new data and migrating to this importance sampling as opposed to just using this click model. Next, the third challenge was how do we run model in production, and operationalization of reinforcement learning techniques. In my opinion, it's one of the biggest challenges, because in theory it all looks very nice, and we can just deploy this agent and it starts to play against historical logs and learn some policy, but in reality things can be much more sophisticated. So building this auxiliary click model is one aspect of it. The second aspect of it is that we needed to implement good A/B testing to compare performance of the new agent against both legacy rule-based solution and control groups. And we also needed to account for the fact that rewards are coming with some delay, because customers, they start to use this offer, start to redeem them with some delay, and we need some prolonged period of time to actually make some conclusions regarding the performance of these offers, how they impact customer lifetime value and longer term behavior. So the way we did it, we actually decided to replay logs with some delay. So once we collect logs from production system, we replay them with some delay because we need to wait until we will know our rewards, and then we join our rewards into this log. So it's still not really real-time learning. And finally, the third question that we are still trying to figure out, the solution for which we are trying to figure out, is how to deal with non-stationary data, because the environment changes over time and there is some trade-off in the sense of the more historical data we use, the more historical logs we replay, the better the results in general, unless this historical data become irrelevant and we need to decommission it. So essentially we need some historical data retention policy, and we need to determine what exactly this policy is, what are the parameters of this policy, how many weeks or how many months of data we need to retain to achieve optimal performance. And this is still an open question that requires substantial research and requires to operate system probably in production for a long time. And finally, the last group of challenges is about accurate modeling of the environment, because conceptually the problem of environment modeling can be, it seems relatively straightforward. We have this environment with customer states, we have many different offers, which are our actions, and we just represent customer as a feature vector, and then we learn which offer we provide, which action we take. But in reality, it's more complicated than that. One of the problems is that we actually might be interested to learn how offers that we are providing to the customer compare to no action baseline, and in general we need to include no action option into our action space, which to be honest, in this project was not obvious from the very beginning, so we figured it out only at some point. And then the second challenge is that the action space can actually be more complex than just offers. For example, we can have multiple touch points, multiple channels through which we can interact with the customer, as it's shown here. And we need to choose not only our offer, we need to choose our touch point as well. The system needs to be a part of the policy, or we need two different policies, one for choosing the touch point and another one for choosing the offer. And it of course adds a lot of complexity, because if we increase the dimensionality of our action space, it imposes much more statistical computational challenges. And again, this is something that we are still trying to figure out. This appears to be a very complex problem. But in general, the system it proved itself to be efficient in several ways. In particular, it provides strategic optimization out of the box. It allows us to simplify to some extent policy development, model development, because once we jumpstart the system, we can just channel our logs into the reinforcement learning platform, update the policy, and deploy it back to production, which is quite different from traditional modeling pipeline, which is all manual and requires a lot of manual, at least monitoring or interactions. So in that regard, the solution is generally, we consider it very interesting, and it's definitely a large step forward comparing to traditional models like lookalike models or collaborative filtering models, at least in some sort of problems. So from the technical design standpoint, the design that we eventually implemented, it's summarized in this slide. It basically just captures everything that we talked about in a few previous slides. So we the way we implemented this project, we started with building this environment simulator with our click model based on historical data. Then we used reagent to train the model based on using this environment simulator. Then this model, some evaluation tools were implemented to compare performance of this policy with our baseline click model. Then this model was deployed to production, and some targeting server used to do A/B testing, used to apply some business rules on top of policy to somehow constrain the actions that we can take, which of course is a very good idea in production applications. And this targeting server was integrated with transactional system, and then we received back our logs, and this is how we closed the loop. And we used the logs to retrain our policy again, and deploy this policy to production again, and repeat the whole cycle. Yep. So to summarize key lessons learned from these two projects, from these two case studies, there are several typical problems for which reinforcement learning can be beneficial in enterprise settings, and in personalization problems in particular. So first of all, if we have some dynamic content like news feeds or banners that are changing rapidly, or we have many new users that are coming to our website, for example, then we can use basic reinforcement learning techniques, in particular multi-arm bandits, to do this optimization. This can be this is most natural solution in that case. We are not pursuing strategic optimization, but we're just trying to dynamically learn the dependency between customer properties and content properties, and authors or personalization actions that we take. If we are interested in strategic optimization, like optimization of multiple steps, multiple sequences of authors, then in most basic form, we can use fitted queue iteration to do that. It will be just natural extension of lookalike models, which we can implement essentially using traditional infrastructure, traditional workflows. It's essentially about defining and redefining our target metrics in more sophisticated and more clever way. And finally, if we would like not only to do the strategic optimization, but also do dynamic optimization, and also looking to simplify our modeling process, our modeling workflow, then we can use some turnkey reinforcement learning platforms like Reagent to essentially to consume logs from our applications written in a certain format, and then producing some personalization policy, deploying this personalization policy back to production, and updating it in iterative way. And of course, all these three options are very beneficial in their own applications, depending on the application, of course. And in general, they are superior to traditional techniques. For example, fitted queue iteration, in general, it will outperform, and it does outperform lookalike modeling. And in dynamic environments, multi-arm bandits, they typically perform better than traditional offline personalization model learning. Yep. So, but still, in terms of challenges, still there are a lot of challenges with regard to how we estimate performance of new policy, how we deal with non-stationary data, how we operationalize the whole thing, how we deploy it to production efficiently, how we bootstrap the system. But hopefully these challenges will be solved. I do not believe there exists like a simple answer to these questions now, and many companies, they are trying to experiment with these techniques, but still it remains, I think, quite challenging to do it in practice. Yep. So thank you for attention, and please ask questions if you have any. Thank you.
Awesome. Thank you so much, Ilya. We're going to hop right into the questions that came through. So I'll start with one of the questions that came through for Jeff. And Jeff, that question is, can you talk about how you partnered with Grid Dynamics teams to optimize your targeting strategy? And how critical was Grid Dynamics to your end product / what did they bring to the engagement that CVS did not have internally?
Yeah, thanks for the question, and it's a great question. And I'd love to have some collaboration with Grid Dynamics on a couple of issues. Maybe that will happen in the future. Unfortunately, so far we haven't done any collaboration yet. We will try to talk about it later and see what happens. It seems like Grid Dynamics has developed lots of analytical suites, and then that could be applicable to let's say the retail field. So we have multiple lines of business, and maybe there is some room for collaboration for sure. Thank you.
Awesome. Thank you, Jeff, for that answer. Another question that came through for you. What are the unsupervised algorithms that would best suit for product recommendations? And can you explain more about how you or your team designed a predictive package without splitting?
Yeah, this is a great question again. Let me, I think there are two questions in this one. The first one is talking about unsupervised algorithms for product recommendation. And then I'm not sure which one is the best one, but we did have some, some solutions like that before, like I call it the previous versions, developed internally and externally by some partners. And then, the traditional way, all the way before my version is that they build using a traditional way, say hi for product, let's say cosmetics. And what is the probability for customers to buy cosmetics? What is the probability for customers to buy, say, a toothpaste in other products, so on and so forth. That means if you have hundreds of categories, products, so you have to build hundreds of models individually, and then use them as a suite, and then to select the highest score of that product to recommend. I hope I made it clear, right? You have you might have hundreds of models for hundreds of products, and then that's quite some job, and then it requires a lot of resource and time consuming. If you updated that, it could be a nightmare as well. So, and then fortunately, I was able to develop myself, an algorithm for that. And then sort of like it's a unsupervised in the big data approach. It's like a combination of machine learning and big data approach. That means each record of the transactions our customers made, let's say, in 12 past months, was used for that purpose. All of them. We have close to 80 million customers in our database. Think about the volume of that. Each of the transaction record was used for that. Big data and machine learning approach. And hopefully I answered that first question. The second one, I designed the offer optimization package. That's different from the production. Offer optimization means, I give you like a 10% off, or let's say $8 of 50 you spent. That's called threshold. Percentage offers, threshold offers, and we have other offers as well. Which one we should give that to the customer? And then, so this is a kind of optimization. Traditionally, all the previous versions are built internally and externally, splitting, samples of customers. Let's see,
Why they were doing so? Because we, for each campaign, retail campaign, we want to measure the lift. Lift means, okay, what is additional sales? Additional sales in terms of dollars, right? Additional margins earned, additional sales happened. So additional means we compare with the test group with a control group. You have to measure that. In the traditional using dynamic decision tree, using let's say k-means, and then that involves splitting the test group and the control group at the same time, simultaneously, right? And then the problem with that is the further you split, the smaller samples you are getting, and then the less reliable of the KPIs, the lifts are. So for those of you who took statistical courses at the college, for sampling, there is a statistical testing, significant testing associated with that, right? Certain sample size required for a valid readings, from the samples. So that's the problem. So you split it further and further, and then the data set is getting smaller and smaller. The numbers are just bubbles. It's no longer valid anymore. So you are modeling on the bubbles, and then you can imagine what kind of model you are getting. So the results may not be that desirable. And then that's the facts. That's what happens. So what I designed, said, oh, yeah, that's what happened. And then I had a deep learning of customers' shopping behavior, redemption behavior, and based on the campaigns, like with the campaign, without campaign, and there are some effects after the campaign, and then based on different segments, and then to understand the key objectives of the campaign pattern, frequency, things like that, all things put together. So, deep understanding of the customer's shopping behavior, again, redemption behavior, and the campaign objectives, campaign pattern, and the channel pattern, and design a package. It's completed at the customer level. Let's say a customer like Julia, we're not comparing you with the others. We just say, hey, what offers is best for you? Best means, you get some discounts. That's good. You are happy. And then for CVS, we got some margin of sales increase as well. It's a double win situation. So that's how I designed this package. It works like a charm, basically. Hopefully I answered that question. Thank you.
Awesome. Thank you so much, Jeff, for that answer. Our next question is for Ilya. Someone asked if you can explain the state and action space for the second case study and how the problem statement on the first case 2 slide again.
Actually, in both of these projects, their state and the action spaces were defined similarly. State space is basically a representation of the customer at any given point of time. That includes different static features like demographics, that includes some behavioral features like transaction history, purchases, and it also includes previous interactions with these customers in terms of offers or other incentives. So all these different features are combined in the state vector. And the action space is the space of possible offers. So typically, in both of these projects, it was just the space of offer IDs, but in principle, it can be more complex action space that can include offer properties like is it a dollar off or is it a % off and so on, and what's the category of the offer and so on. So to the second part of the question, what was the problem statement? The problem statement in these both projects, it was somewhat similar. The difference was mainly in the industries, and the dynamicity of the environment. In the first project, we were solving problem of promotion targeting for CPG domain, and we were just researching and analyzing historical transactions. We did not really do like active exploration of the environment, so we were using these kind of reinforcement learning techniques only for strategy optimization or for sequence optimization, but not for exploration of the environment, not for dynamic optimization. In the second case, we were optimizing digital offers for digital products. And in that case, it was a more complete reinforcement learning solution in the sense that we were looking to optimize both sequences of offers, that is doing strategic optimization as opposed to myopic optimization, but also we were trying to make the system to work more in real time and get feedback more instantly and retrain our personalization policies based on this feedback and so on, as closer to real time as possible.
Awesome. Thank you. And we've gone a bit over time, but we'll take one more quick question. Is the underlying platform Pega's decision management? And that question's for Ilya again.
No, in the first project, it was open source implementation using just basic Python libraries. Essentially, we used just supervised learning models and applied them iteratively to implement fitted queue. In the second project, we use Reagent, which is also an open source platform originally developed by Facebook. So here, in general, both solutions were implemented using only open source tools.
Awesome. Thank you. And thank you to both of you for being here with us today. There's a couple questions that we didn't get to, so we'll definitely follow up on those offline. And then just a reminder, we will be sending out the recording to everyone who registered, so you'll receive that within the next couple of days. And be sure to register for the next webinar in October. It's going to pop up after we conclude this session as well. So be sure to join us there. And thank you, everyone, for joining us. And we'll see you on the next one. Bye, everyone.